एक मिनट सर।
कोई आया है?
नहीं, अभी तक तो नहीं आया है। एक मिनट सर।
कोई आया है?
नहीं, अभी तक तो नहीं आया है। सर, स्टार्ट कीजिए सर। एक मिनट सर।
All right, is there anyone there?
नहीं, अभी तक तो।
So we wait for a little while till someone joins.
नहीं, अभी तक। सर, स्टार्ट कीजिए। एक मिनट सर।
Right, is there anyone there? So we wait for a little while till someone joins.
I think somebody has joined. I think somebody has joined. While some more students join us, maybe we can have some discussion regarding this course. So, uh, Professor Gupta, there is something which intrigues me a lot about this approach of dimensional analysis. It's quite useful, quite easy to do. I mean, always there are even stories about people achieving great results with so little effort. I mean, commendable results with just a little bit of back of the envelope calculation, calculating. You also, I think you have also shown some examples in your course, like calculation of yield of a nuclear explosion and something. But one thing which intrigues is that, I mean, theoretically, while maybe we
Go
can
ahead.
yeah. So what happens is that theoretically it's very nice that we form pi groups and reduce the number of independent variables we need to vary while doing an experiment. Uh, so and save our resources for doing experiments. We just vary the pi groups and see relation between them, and that gives us um, how a physical phenomenon is dependent on the independent variables. But one thing which often occurs is that we are limited uh, in in real situations, in experiments, by the parameters that are physically possible to vary. For example, you can have velocity as involved in two different pi groups, and it's the main thing that you can vary in wind tunnel experiments, for example. So suppose we want to do wind tunnel experiment on, say, vortex induced vibration. So this velocity will occur in two different pi groups. It will come in Reynolds number. It will come in reduced velocity also, which is a way of non-dimensionalizing natural frequency of your structure. So in this case, changing the velocity will always change two of these things. Similar kind of thing is seen with Reynolds number and Mach number, Reynolds number and Fruits number. So you have a common variable between two different pi groups, and it's the main variable that you can change. It's very hard to change Reynolds number by changing viscosity. I mean, how many different fluids will you bring to the for the experiment? I mean, we are doing experiment in the air. It's quite easy to adjust the speed of the fan, but it's not possible to change the density or the viscosity. Similarly, in case of fluid number,
So
it's not possible to change the gravity. It's velocity only most of the time that you can change. So by changing velocity, but we are getting really, I mean, we are not getting relation between two pi groups by holding others constant. You are varying two different pi groups at a time. So that's one of the problem that I see with this kind of approach. So and I mean, what I have seen is that people develop some heuristic or some, phenomenological or whatnot kind of model to get out of this situation, but there is no general roadmap. So what are your suggestions for such situations? How can we adapt to this kind of paradox, or this kind of scenario?
see, uh, the method to deal with this is what is called relaxation of rules, relaxation of modeling rules. In this case, there are various methods of relaxing rules. You artificially create an experiment with tall chimneys. And when we do experiment with tall chimneys, the chimneys are made of concrete. Obviously, we could not, in a wind tunnel, we could not accommodate chimneys made of concrete. So we use fiber to make chimneys. But then we had what we call the detached masses. We want to add up. So we used a rubber lining on these chimneys, which added mass did not contribute to uh, stiffness. So it's in the same manner like you do experiments in ships. When you do in the ocean, experiments on ships, you make a small model of a ship. You run a problem. The stiffness is scaled by a different factor. Then is the mass. So the stiffness would go like uh, L square, and the mass goes like L cube. So to do this, you use model. You take little pieces of masses and you disconnect them. You string them on a bar, and that way you could manipulate the stiffness separately from mass. So there are a lot of techniques. This is a book, famous book by uh, Ibori and Shuring, which has a huge chapter, something like running into 200 pages on different relaxation techniques. I would, in course, come slightly on that uh, topic. And so we have about 3 lectures which we cover on using relaxation. And relaxation is you relax some rules, you relax something so that your model works in certain regions and for certain quantity. And you can get better results out of this. Now, another thing that is the power of initial analysis lies not so much in being able to conduct the experiments. It lies very much into determining what approximations are valid. You cannot do numerical analysis unless you are doing a full Navier-Stokes equation solution. You cannot, if you are making any kind of approximation solution, how do you justify that approximation? The method of just approximation comes through dimensional analysis, which forms a large part of this course that I'm teaching. The week number 5 and 6 would be devoted to approximations. How do we use approximations? How you use dimensional analysis to make approximations? Do I get some?
Yeah.
Do you get a flavor of what I'm trying to say?
Yeah, sure. That was enlightening. So, I mean, that of course reminds of the classical work of Prentill,
See,
that is
there is
starting
a
from.
also I've done some work in numerical analysis where we neglected some terms. Then
Yes.
what I do at each step, I would calculate the value of the neglected term itself after I made the calculation. Then
Okay.
the term that was neglected, I'll put in the values there using the result already obtained. So in
Uh,
explicit form, I would obtain that estimate and would verify, keep on verifying that this value remains below one or below one because you normalize everything. So all your terms should be of the order one. So if it remains below one, always, then your approximation uh, appears to be justified. But if at some places, at some locations, the value goes above one or near one, then you will have to analyze there very quickly that do you need to change approximation in this region. So then you use some kind of a split field that you use a different approximation in a different region, either temporally or spatially. There
hmm.
was one example of Dr. Jason Nivasan had a student who did uh, work on analyzing the heat transfer in a rice husk chula, and he
Okay.
made approximations. But I was an examiner of the thesis, and I could show to Nivasan that the approximation breaks down, and this I could prove only by making a student do some calculation in which he was tracking the value of the terms which were ignored in the main equations, which appeared very reasonable that you can ignore them. But then when we actually calculate the value of the ignored terms, they were quite significant. And because their significance, he had to work, which very brilliantly did the work by splitting the field. It very brilliantly did the work.
So is it similar to what we call as meshed asymptotics, where in different fields you use different
It is match.
scalings?
Match asymptotic is mathematical. Uh, uh,
You are talking about numerics.
I'm talking on numeric. I'm talking even numeric. But match asymptotic is a solution. The indication of where the match asymptotic is to be used. Singular
Yes,
perturbation, where it is to be used. How do you get the indication? In fact, if you
from
look
the
at the Prandtl
dimensional
theory,
analysis.
if you look at the Prandtl theory, Prandtl from dimensional, he figured out that there should be a boundary layer. He
Yes,
figured out from dimensional analysis, or we don't call it dimensional, we call it normalization. From
normalization.
normalization, from normalization equation, he figured out normalization is dimensional and non-dimensional. So when he non-dimensionalized and normalized, then he figured out that the approximation that viscosity is small or Reynolds number is very large could not be valid in a layer near the plate, near the wall.
True.
So in
Um,
fact, uh, and that's a match asymptotic expansion. So a boundary layer theory is the first example. Then
yes. Yeah.
uh, you use shock waves in your numerical analysis. If the shock wave is free flow, then those shock waves are are analyzed differently. There are different approximations through the shock layer against, quite like mesh asymptotic.
Same goes for Buznask approximation. Long time ago, I mean, as an undergraduate project, I did this thing that comparing how good Buznask approximation is for different
Which
uh,
approximation?
Buznask approximation
Which approximation?
for non-isothermal flows. Buznask approximation.
Business. Yeah, yeah. Business approximation. Yes, business approximation also is very interesting. Yeah, same thing, same kind of thing, same kind of
So,
thing.
so just so I had this thing to track that how good is it for how good Buznask this approximation is for different amount of heatings, and what we found
Absolutely
was,
correct. Absolutely correct. Yeah, beautiful. Mhm.
so what we found, we did not publish it, but what we found was that for Nusselt number it was quite bad early on. I mean, as we increased heating, but for drag and lift, it was still okay. So I don't have any physical explanation to that why it occurred, but our suggestion out of the, I mean, as a conclusion of that work was that for Nusselt number, the Buznask approximation breakdowns much earlier
This is the
than
work you
for
did as an
drag.
undergraduate.
Yeah, as an undergraduate project.
Yeah,
So I was at AMU that time.
AMU. Who was your help guide there at
Professor
that time?
Professor Nadeem Hassan was my supervisor
Nice.
for that. So he
Nice.
he
He
developed this
does great work.
PVU M plus PVU
He
M
does
plus
great work.
scheme. He was using his own scheme. So he asked me to do this. After that, he did. I mean, several of his students did some PhD thesis on that. I mean, he has several students who did PhD and master's thesis. I worked as an undergraduate project student, but then I moved to Kanpur to work on FSIE.
So when were you at Kanpur?
So I was between. So I joined there for MTech in 2012,
2012. Okay.
and from there, I mean, I heard a lot about you from Professor Sanjay Mittal.
I already left 12 years ago. Yeah.
So he was like, I mean, he used to tell that maybe he was inspired from you for joining Minnesota. You were his inspiration for applying to Minnesota. Anyway, so another thing, as we were discussing about these relaxation methods, so one method that I came across in I first came across in one of the assignments in a course that I was assisting as a TA, but later on I found that in Facebook, the method was to split, you know, for us it was for ship analysis of ships in a towing tank, or and what the author was doing was, of course, Faye is famous. I mean, he has background in naval architecture, though he's famous as fluid mechanics author. So he suggested using different models for drag. So he split the drag into the that friction and wave drag, and then he use different models for them. For skin friction, he used some simple model using just the boundary layer over a plate or something, and for the other part, he used dimensional analysis.
Yeah, that's a classical solution. Uh, and it is Froude. Froude himself, William Froude, more than 100
Okay,
years ago. More than 100 years ago did
okay,
this. So what they did was the drag was consisted of two parts. One was the skin friction drag and the other was wave drag. So he says what it did was he on the model he modeled by matching Froude number so that the wave drag should follow a modeling rule, prediction rule. So using a model, he finds a total drag on the model. From the total drag, now subtracts the friction drag, that is the skin friction drag, based on simple calculation of boundary layer on a flat plate
Yes.
on the sides of the ship and on the bottom of the ship. So treating them as a flat plate, he calculates the friction drag. He subtracts friction drag from the total measured total drag. So that would be measured wave drag. Now, wave drag is scaled using the fruit analogy. So he got an estimated wave drag for the prototype ship. Then from the or to this he added the calculated the calculated friction drag from the boundary layer theory. Added that, so he obtained a total drag, and the results were within 10%. This was done in 1880, 1890, 30 years ago.
So, is there any general framework for this kind of analysis, or as you suggested in the book on
General
relaxation,
framework, it
or
is
it is
to
every case by case? It's always
it's a
case by case.
case by case, but when you work enough, you start getting hints.
You get the
In
feel of
all
the
of them,
problem.
they are general, but it cannot be a mechanical process that you put in input there and
Okay.
the output comes out of it. You do it, you read up. So I would recommend you that if you have time, get this book by Mori and thing. Uh, 2 years ago, this was available easily on website. But if you uh, send me your send me an email, I could mail a copy, a FDP
Maybe
of. I could mail a
maybe we can
PDF.
maybe we can put the name of this book in the description. Uh,
It is there. It is there. It
okay,
is
it is
there in
there
the. It is there.
in the course flyer.
I can't do with this because this is it's a very remarkable book. It is there. But
Okay.
what I'm saying is, if you want a PDF of this, I can send you a PDF. It's not a proper PDF. It's a camera
Okay.
copy. So it's a scanned camera copy, not a PDF, because there are too many handwritten equations. So it could be you could use an OCR to convert it. So it's a camera copy. If you are interested, send me your email, and I would mail a copy to you.
Okay. Thank you.
Also, yeah, yeah, okay. I'm revising the textbook of mine, and is a major revision. And I
Okay.
wrote a new chapter on dimensional analysis and on approximations. So those things I'm distributing freely. The book is yet to come out. The new edition is yet to come out, but the manuscript I'm sharing, and it is available in this course. In every week, I'm releasing one chapter which is relevant to that fluid mechanics book.
Okay.
So you may download it from there,
I'll surely
or if you
look into it.
if you want, I could send them those two ones as well to you.
I'll surely look into that.
So this Inspire Professorship, what does it do? What do you do? What do you need to do for that?
So it's like it's a it's a fellowship from DST. So what they do is they ask for researchers who are about to complete their PhD or who have completed their PhD under 32 years of age. They ask them to apply to DST and write a project on which they will work on, and then they shortlist based on their resume and publications and all, and their past record, academic record, and from there they shortlist, and then we have to give an interview in front of a panel.
They attach you
And
to department. They attach you to department.
no, so they just give us a fellowship. In the end, DST will just say that you have been selected for the fellowship. Now it's our own responsibility. DST won't take responsibility for that. It's our own responsibility to find an institute who is ready to host. all the funding will be from the DST, including our salary at par with assistant professor, and a project of 35 lakhs for 5 years. So the DST gives all the funding,
So now
but
you
we
are
have to
attached to
fund the
applied
course.
mechanics or mechanical?
Applied mechanics.
Yeah. Now you are attached to applied mechanics or mechanical?
I am in applied mechanics.
So you are required to teach as well?
So it's up to the department. It's for the department to decide. In my case, yeah, fortunately, I am teaching. So this semester, I am taking advanced dynamics in applied mechanics. Tech course.
Fine. Dynamics.
Yeah, advanced dynamics, which is basically a vibration course.
Yeah. Quite different from fluid mechanics from your specialization?
Uh, because I did fluid structure interaction, and for that I studied lots of vibration and structural mechanics and finite elements. So I have some background in structures. In my masters and PhD, I learned sufficient fluid mechanics in my undergraduate, and later on I did few courses in MTech on fluid mechanics. But then my most of my courses in PhD and some of my courses in MTech were on vibration and structural mechanics and FEM and all.
So
So I
Sandeep,
have
can we
this.
close? Sandeep, can we close?
Yes, sir. If there is no any question, then we can close, sir.
Yeah, I think we can close this. Another
Yes, okay, sir.
Okay, it was
Okay,
nice.
sir.
It was nice talking to you, Fakan.
Yeah, nice to meet you, sir. I was also thinking, of looking for an opportunity. Professor Sanghi also talked about you. Professor Mittal used to talk about you. So I was also uh, uh, looking forward to see you and interact
Yeah.
with you. I am always, sir, I am always, attracted and intrigued by people who have great physical insights into problems. I follow some of the researchers who do these kind of things, and I have always tried to develop them myself, even though I am not quite good at these things. I mean, my in my undergraduate training, what I learned was to use the whole huge model. The approach that Professor Nadeem Hassan has is to use all the terms. He says that I never use approximations. I use as much general model as possible. So I got that thing. So but I credit to him that he trained me in writing full models with ease, and finding their non-dimensional numbers and all. But I have always tried, but never developed uh, this knack of finding what is important and what is negligible. As you said that you try lots of problems and from there you gather on, but it's like, it's quite a skill to master. It's a nice skill to have.
You see everything, you think what you do in a numerical analysis is easy to master.
Yeah,
Everything is difficult to
everything has
master.
everything is difficult to master, but I am like I'm trying to see how people achieve this kind of thing. I like analytical solutions in the end, even though I am a CFD guy, but I always try that. So I did some course on perturbations also, even though that is not trending nowadays. When these computers came, many people, Professor Narsimha, Rodham Narsimha, once said in an interview that his professors at Caltech were very apprehensive of these computers coming, and they will be, ruining the minds of researchers, that they will get habitual to calculating everything instead of having feel of the equations, and having the feel that what is important, what is not, how can you simplify it to finally to an analytical solution. And that's what we have seen now. That has occurred. People do acknowledge that it's
You
good
see,
for engineering.
I have a training. My PhD advisor was a professor named Ted Wilson.
Okay.
Um,
Yeah.
he worked in biomechanics largely, but he was a person who always back of the line. You could I would work for 1 week and get a result and he would look at the result and he says it doesn't look all right. I think the power of uh, V is kind of tricky. It should be a little different power. He
Oh,
could do this. He had a feel of equations. And what I gathered, he never explained, but what I gathered from this, it was basically through approach of normalization, that
okay,
he would understand what should the factors that should be involved. And it's some kind of dimensional argument. He was always using some kind of dimensional argument. And by following his logic, and he never explained this, but he was quite transparent when he did these things.
okay,
So when he did this thing in front of you, you could figure out how his mind was working.
okay.
And when you figure out when his mind was working, you get to learn those things. So I was lucky in that sense.
People who are doing
All right, fine.
analytical
Nice
things and all
talking to
this.
you. Thank you.
Yeah.
And
Thank you, sir. So I'll
say
I'll look
bye-bye.
into that book. I think I'll
Okay.
find from the flyer. I must have looked at the flyer, but it's good that